So now today we're going to add two more. We're not going to do that much. We're going to use them in interesting ways. We're only going to add two. Okay. The first one has a horrible name. Is the continuity equation. Okay. Continuity equation. It's really a fancy way of saying the conservation of mass. That's really all it is. The conservation of incompressible mass. So I would say it like this. A bit of fluid, computer science people get excited, a bit of fluid retains constant volume as it flows through a system. I can't write today. Through a system. That's it. Constant volume as it flows through a system. So let's see if what formulas that gives us. Okay, so we've got, let's have a system that's a little bit interesting. It's like a narrow pipe over here, and then it expands to a wide pipe over here. Okay, my bar for interesting is not high. Okay, the fun parts are over. Okay, here we go. So the narrow part of the tube has a cross-sectional area A1, right? So there's the narrow part of the tube there. And the wide part of the tube, oh, so much chalk, is A2. So clearly, A2 is bigger than A1. Hopefully you can see that. Right? Looks like we're at Home Depot buying PVC pipe for your high school something or other. Let's see. So what we're saying is we've got to look at some volume of fluid. Okay, so we're talking about volumes here. So let's say here, the volume that goes past A1 in delta T. Could we figure that out? Well, the volume would have to do with like the flow velocity, how fast we're flowing, right? Because we're doing fluid dynamics. So the velocity V is just how fast the liquid's going. So it's the same old V that you're used to thinking about. Okay? So we would say this fluid is going at V1, right? So in time t, the fluid that was here is going to make it to say here. In time delta t, it might make it to here. Okay? So here is your volume. The volume past A1 in delta t, there's V1. This is like delta x1. And they all go together. You know, V is delta x over delta t, or delta x1 is V1 times delta t. So if you wanted the volume, then the volume 1 is what? It's just this area 1 times the delta x. So you could write it as area 1 times delta x1 or area 1 times V1 delta t. Either one. I forgot what I wanted to do to get started. I wanted to call it delta x. Okay? The volume of 1 is the area of 1 times delta x of 1. So all we're saying is it's flowing. If you go some distance delta x, some area A1, that's the volume. That's all we're saying. Okay. Now, what about over here? Over here, let me give myself a little more room here. Make it a little longer. Put the A1 over there. Sorry, that's A2 now. Right. So here, the same volume that went here, it's the same volume that's going to move here. Right? So you can see it must be much shorter. It's got to have the same volume, so it's a much smaller little area we're going through here. Because on here we would say in the same delta t, then it's also true that, we have V2 equals A2 delta x2, right? So here, really short is delta x2. And it's also at a different V, right? It's not the same V. Okay, so no relationship between them yet. Okay, here it's flowing at one velocity, here it's flowing at another velocity. Here it'll cover V1 in A1 delta x, here it'll go through V2 and A2 delta x. Okay? But those happen, but to conserve, to conserve volume, those are in the same delta t. It's sort of how you would think about it, right? So you could divide both sides by delta t, and you could see that A1 delta X1 over, or you just say sort of A1, let's not, delta X1. The volume you shoved in here has to come out there, equals A2 delta X2, right? Those are the same, right? Those volumes have to be the same, and they happen in the same delta T, so you could put the delta T under it. Because it kind of depends on what relations you want. Sometimes you want a relationship between the volume that changes, sometimes you want the velocity. So here we're thinking about the general laws about the velocity. So you can see delta X1 over delta T, that's V1. And delta X2 over delta T, that's V2. So you get the continuity equation is simply A1 V1 equals A2 V2. That's it. Okay? So A is cross-sectional area and V is flow velocity. So that was an attempt at a geometric description. I think it sort of made sense. But now just think about it this way. Anywhere you go, it's got to have the same amount of material flowing here that it has flowing here. Right? This is, what is this in? This is in meters per second. Meters squared times meters per second is meters cubed per second. This is basically a flow volume, a flow rate. Okay? Both of these equal Q, which is a flow rate. We don't use it much, but that's what it is. So you got to have the same amount of material flowing here that you have flowing here, because you got to conserve mass and because it's incompressible. The volume has to stay the same. So if the same amount of mass goes in here, it has to come out there. So now we have a second equation. That's it. A1 V1 equals A2 V2. That's all there is to that one. So this one is continuity. A1 V1 equals A2 V2. As something flows. All right? Interesting, I say. You can have a demonstration of this, and I couldn't pull it together in time because stuff is happening. But if you ever see water flowing, right? So if you ever have this case where you're looking at, like, just go to your sink tonight. Here's your sink, right? And the water comes out. And turn the sink down where it's nice and laminar, right? If you look at it when it's nice and laminar, you got to get real close. That's why I didn't really do it for you. As you can see, it actually is getting narrower before it breaks up into little drops. And the reason it's getting narrower is it's speeding up, right? So here, gravity speeds it up, makes it fall faster. So therefore, if it's faster, let's see, if A1 V1 at the top is some value, that value has to equal A2 V2. Well, if V2 goes up, A has to go down. Right? So columns of water that are following actually do get narrower. It's a little hard to see, but it really does happen. Okay? So go look for that.